Great. Okay, so welcome to the second session of this introductory mini course on coarse geometry.
Let me introduce you again.
Yeah, great.
So welcome again. This is the second talk by Sergio. So he will talk on coarse-cohomology and the course category basic properties.
Yeah,
So
thanks
yeah.
for the introduction. Okay, so I will now share my Blackboard, and I'd like to let me know if you cannot see something clearly here. I'd like to begin with a small reminder of these more important bits that we saw the other day. So our idea is that with every finitely generated group, we can choose a finite generating set. With that, we can define a connected graph, and then by measuring lengths of paths in this graph, we can induce a metric space. And the point of this is that we want to translate algebraic properties of the group in terms of geometric properties of this metric space. Okay, so also one important notion that we introduced is that of the quasi-isometry. So quasi-isometries, that's from the previous talk, these are these maps that allow us to see when two spaces look the same from far away. So it's, in topology, for example, in topology, these homotopy equivalences would be a way to tell that two spaces can be deformed into each other. This is an analog, but from far away. There is no continuity, just distance. Also, we saw that if we only want to do geometry at infinity, the choice of the generating set is not important. We prove the following lemma. If I change the generating set, then the identity between these two metric spaces is a quasi-isometry. So any geometric property that I talk about is going to be independent from the choice of the generating set. Also, I left some exercise for you, just in case you were interested, and the exercise was first to find a finite generating set of this group. This is the group of isometries of the integers. And then with that, you can consider the Cayley graph and understand its geometry at infinity. I now want to make a question. Does anyone wish to share this solution or their idea with us? I will wait a bit if someone wants to share it. Okay, maybe not. Okay, so here goes some small hint. So this, again, this is by definition the group of isometries, so distance-preserving bijections of the integers. And there are two kinds of such isometries. Two kinds of isometries. The order-preserving one, or orientation-preserving, order-preserving one. So these are basically translations. So it's of the form, I send every integer to x plus b. So yeah, something like that. And under the order reversing isometries, the orientation reversing, these are symmetries. So for a symmetry, we would have one center. Let's say this is the center of the symmetry, and then these two are interchanged, this one is fixed, and so on. Yeah. So with this idea, you can consider the following set of generators. This is also called, this group of isometries is also called the infinite dihedral group. It's because you can imagine that it's a dihedral group, but with infinitely many, infinitely many sides. That's kind of the idea. So this is now generated by a translation of one unit and a symmetry. So here T is, it's this map that sends every point to the next one. And S is any symmetry. Whatever symmetry you want, you can take. Then for simplicity, I will take the symmetry based at 0. And then, these are two generators of the group. With these two generators, you can draw the Cayley graph. So the Cayley graph, you can believe me or not, the Cayley graph looks something like this. Okay, yeah. So, So translation, if you draw the Cayley graph, there is a row of isometries that are connected by translations. So I will use the green color for the translation, and then these are connected like this, and so on here. And now the symmetry here is connecting each of these two vertically aligned points. And now this goes on forever. This goes on forever. So now this is not a rhetorical question, it's a question for you. If we look at this space from infinitely far away, what does it look like? I will wait a bit. Maybe I draw something, but
R?
Again?
Maybe the whole R?
Yeah, the real line, exactly. Perfect. Yes. Right. If I zoom out, these two horizontal lines seem to be closer, and then it's something like this, right? If I zoom out more and more, it seems that these two lines collapse into each other. If I take this process to infinity, I'm left with a real line, right? Great. So it means that if I take, again, now my group G is the infinite dihedral group, and the finite generating set is this translation and the symmetry. Technically, I did want this to be symmetric, so I will also take the inverse translation. And now the Cayley graph of G with respect to S, we see it is quasi-symmetric to Z. To the real line. Yeah, so the real line, which is also quasi-symmetric to Z. Yeah.
Yes, Sergio, could you please a bit, fine. I just want to see these maps, these group elements, just T and S, X goes to minus S. So
you want to see
you have these two horizontal lines. So the above one is for positive thing, or below one for the negative integers?
what are the precise elements of the group, right?
So yeah, I just want to know these vertices, what they represent, like 0, 0, 1, 2, 3. What are the things? I just I'm not able to kind of see it.
Oh yes, so let's be then very precise. What are these points, these elements of the group, right? Well, on one row, you will have the order preserving isometries. On the other row, you will have the, it depends. So let's see. So let's be precise here. Let me write the set of isometries explicitly. So all of them are of the form f of AB. Yeah, and this sends x to A times x plus B, where A is either 1 or -1. This depends on the orientation, whether it preserves orientation or not. And B is translation by any integer. Right, so I can identify, yeah, I can identify, yes?
Yes, yeah.
Okay. So I can identify every such map as a pair AV, right? So let's see an example. So let's say I can put the identity wherever I want. Let's say this is the one. This is the identity. So the identity is the element 1, 0, right? 1, 0, y. Well, yeah, f of 1, 0 sends x to x. This is the identity. And how does composition work? Well, f of a prime b prime, f of ab sends x to a prime of ax plus b plus b prime. So if we multiply everything, we get the following rule. So the product of two elements can be summarized like that, right? So I multiply the orientations, so to speak, and then it's the translation part is a prime b plus b prime. So if you use this rule, now you have an explicit operation. So if we use this rule, using the symmetry, I can go from the identity to the symmetry. Now if I translate, I use the translation, I move around, I have -1, 1, I use the translation again, I have -1, 2, -1, 3, -1, 4, and so on.
Thank you so much.
Yeah, you're welcome. And yeah, you see how it goes on forever. So on one row, we have the order preserving isometries, and these are the order reversing ones. Yeah. Great. So are there any questions so far? Okay. Thanks. So let's see one more example of prominent example in geometric group theory, and then we move on to coarse structures already. So this section is going to be this Schwarz-Milnor lemma. So, oops, sorry about that. That was me. Okay. So this lemma, I will just say, and then we will see examples. So it's about how to relate a group to a space when there is a good enough action of this group on the space. So let's, yeah. So let G be any group. I am not assuming that it is finitely generated, acting by isometries on a proper, I will explain all of this, geodesic metric space. So, and we will assume something about this action. So assume that the action of G on X is proper. proper. This means that if I consider any compact set, the intersection of K with it translates the amount of G's such that the translates are non-empty with K. This is finite, right? This is finite. And it is co-compact. Co-compact, that means that the space of orbits, so this quotient space, is compact. We will see some examples now. So this theorem called the Schwarzschild lemma, it says that then G is quasi-symmetric to X. And yeah, it says more. First of all, G is finitely generated. Let's make sense of this. Is finitely generated and is quasi-symmetric to X. Moreover, it gives an explicit quasi-symmetry. Moreover, for every base point, for every choice of a base point in X, the orbit map is orbit map. So I consider all translates of X0 is a quasi-symmetry. So yeah, it has to be an action by isometries. This proper here means that all closed balls are compact and every 2 points can be joined by a geodesic. Yeah. So, okay, let's see some examples. The basic example where we will use it is the following. So I assume a closed manifold. So this is a closed connected Riemannian manifold. Again, closed here is with empty boundary and compact. Then I can consider the universal cover of M. So it's the cover that is, simply connected. And I can endow M tilde with a Riemannian structure. So in principle, M tilde is just a topological space, but we can pull back the differentiable structure of M, and we can also pull back the metric of M using that it is a local homeomorphism. And then, yeah, M tilde becomes a Riemannian manifold. Moreover, this projection becomes a local isometry. So P is now, when I do this, this becomes a local isometry. So, you know, by in algebraic topology, in covering maps theory, we have a deck transformation action on the universal cover. It turns out that this action falls into the hypothesis of the Schwarzschild lemma. So this tells us that, as a consequence, satisfies the hypothesis above. So then, first of all, the fundamental group is finitely generated, and moreover, it is quasi-symmetric to this universal cover. Yeah. Let's see some example of this in action. Yeah, so one example, one of my favorites closed Riemannian manifolds is the circle. So I will take the circle. And yeah, We know that the universal cover is the real line. So now if I pull back the metric, the usual metric of the circle, what I get on the real line is either the usual metric or a multiple of this. So we are not dealing here with any weird metric in the real line. When we pull back this metric of the circle, we get the usual metric of the real line or a multiple. That's important. So now, if I apply Schwab-Milnor, we will get something that we already knew. I get that the fundamental group of the circle is quasi-symmetric to the real line. But we already knew this because this is the integers. Okay? You can think of this projection map as unwinding a real line around the circle. Okay. Yeah. So one example that we didn't know or we hadn't done before is hyperbolic, the hyperbolic case. So I would consider now that M is a closed surface, orientable, and of genus at least 2. So M is something like this. Okay. And there are G holes, so to speak, G copies here. So yeah, and when it turns out that for orientable surfaces of genus at least 2, the universal cover is the hyperbolic plane. So now the universal cover here is the hyperbolic plane. Okay, and this is now regarded as a metric space, right? If I only consider the topology here, this would be the same as a plane, right? But this is not the case. I'm considering the hyperbolic metric here, which is not the same as the flat metric of the plane. So that's why I write it like that. And then, yeah, by the Schwab-Milnor lemma, the fundamental group of M is going to be quasi-symmetric to the hyperbolic plane. And yeah, this is something we didn't know before. If you try to apply this this Schwab-Milnor lemma with the plane, sorry, if we try to apply this with the torus, then the universal cover will be the plane. And then the fundamental group of the torus will be quasi-symmetric to the plane. But this is not something new. This is the set square, and we already knew that these two were quasi-symmetric. Okay. So, so far, any questions, curiosity about this? So I would like to speak about coarse structures already. We will now move on from geometric group theory. Let's motivate it first. Well, the motivation is already there. We had a group. We choose a finite generating set. And so we get a metric space. So now this metric space depends on S, but the large scale geometry does not, right? Because of this lemma we talked about earlier. So I would like to have, can you hear me clearly? The other day there was a problem. Can you hear me clearly now?
Yes, yes.
Oh, great. So I would like to formalize these ideas even further and then associate to this a weaker structure. This is mysterious, okay? What would be this? I want to associate a weaker structure which encodes the large-scale geometry. So I will forget about the metric and I will consider some structure here encoding the large-scale geometry. So that this arrow is not well defined, but this one will be well defined. Okay, this structure will be independent from S. So this is what a coarse structure will be. So what are the actions for a coarse structure? Let's look at a metric space in general. So I want us to think about metric spaces. So now we consider an arbitrary metric space. And I want us to think of the same sets. So for each R, for each scale, for each positive real number, I will define TR, and T stands for tube. This will be the pairs of points. This is pairs of points which are at distance at most R. Okay, so for example, if X is the real line with the usual distance, then this would look as a tube around the diagonal, right? This would look like this somehow. Okay. Well, I actually took it closed, so yeah. You can also take it open, then it's going to be something like this. Okay. Yeah, so what are the properties of these tubes? These tubes are going to measure this large-scale geometry. How? Well, if there are some properties here, if S is less than R or equal, then TS is contained in TR. So there are some properties involving inclusions. Also, if R1, R2 are positive numbers, then both of them, the union is contained in the maximum, in the tube of maximum radius. Right, so if I take the union of two tubes, then I can contain those in another tube. Actually, this is unequal, right? But I don't care. I only want the inclusion. Then what else? You see the diagonal is contained in every tube. Okay. And, oh, sorry, I'm not numbering this. Yeah. The second one, third one, and fourth one has to do with the triangle inequality. Triangle inequality. And I will write an equation and then see what it means. If I consider the composition of the R1 tubes with the R2 tubes, then this is contained in the tube of radius R1 plus R2. So what is this composition here? Well, given 3 points in X, the composition of them, this composition, right? So if this pair finishes where the next one begins, I can compose them as if they were arrows, right? So you can, instead of thinking of this pair, you can consider of this formal arrow. And then you're taking the composition of these two. Okay. So now, now this composition is the pointwise composition. So I'm taking, this is the set of points x1, x3, such that there exists some middle point for which the distance of x1 to x2 is at most r1, and the distance from x2 to x3 is at most r2. Yeah. So it's all possible compositions of pairs here and a pair here, you see? So now by the triangle inequality, the distance from x1 to x3 is at most r1 plus r2, giving us this inclusion here. Okay? And the last one I'm going to consider is taking inverses. So if x1, x2 is a pair of points, then the inverse, again, we're thinking of this as an arrow, so it makes sense that it's just reversing the order. And so I can do this pointwise with a set. So if E is a subset of x times x, I will denote E inverse to be the set of x2, x1, such that x1, x2 is in E. So all possible inverses. So now you can notice that these TR are symmetric. They're equal to their inverses because the distance function is symmetric itself. Okay. So this might seem like pointless observations now, but it explains or gives intuition for the following axioms. So definition now. So I will now consider a set. Definition. So let X be a set. And then a coarse structure on X is a family. It's a family of subsets of X times X. We will call these subsets entourage, or also controlled sets that satisfies the following axioms. Satisfying. So the first one involves the set theoretic structure. So it is closed under subsets. So if E1 is in E2 and E2 is an entourage, then E1 is also an entourage. Okay. Next, finite unions of control sets are also controlled. So if E1, E2 are control sets, then the union is also controlled. Then, so this considers the set theoretic structure, and now we consider this groupoid structure with compositions of arrows. So for the groupoid structure, we need this diagonal. So the diagonal of X we want this to be controlled. The compositions have to be controlled. So if E1, E2 are controlled, then the composition, so again, this is X1, X3, such that there exists some in middle point in X for which X1, X2 is in E1 and X2, X3 is in E2. So then this also has to be controlled. Okay, so again, we can think of this as a composition of errors. And finally, if E is a control set, then the inverse is also controlled. So these structures are commutative or symmetric. Yeah. So this is a coarse structure on X, and then a coarse space is a pair X E. Okay, so it's just a set endowed with a coarse structure. So I think some examples are in order. Right, so the first one is the coarse structure of a metric space. So here's some examples. So the first one is the bounded, this is called the bounded metric coarse structure. Sometimes I will not say bounded and I will just say metric coarse structure. So let XD be a metric space. And we will now use these tubes as before. Then, oh, sorry about the notation here. This is soluble. XD. Okay. So then the bounded metric structure is the following. It's defined as the subsets of the product. Again, a control set has to be a subset of X squared, such that there exists a tube that contains it. So for some radii, for some radius big enough, for some big enough R, E is contained in this tube. So this inclusion can be written as, yeah, I mean, you can read this as the distance of any pair of points being at most R for every pair in E. So an equivalent way of doing this is, yeah, a subset is controlled if and only if the supremum of all the distances in this set is finite. So this set of distances is uniformly bounded. Yeah, it's the same. Okay, so if you see our intuition before with tubes, the properties that we were looking at are not exactly those of the coarse structure, but if we take all possible subsets of the tubes, then we get a coarse structure. Okay, so the triangles, the tubes are not closed and they're taking subsets, right? Because I can, for example, this is a tube, but then I can have some subset, weird looking subset like this, right? Inside, and this will also be controlled. Okay, so that's the bounded metric coarse structure. And in particular this is what we're doing for geometric group theory. So for a finitely generated group, we're choosing a finite generating set. This gives me a metric space. And then what I'm taking here is the bounded metric structure. This gives me coarse space. So this is a metric space. This is a coarse space. Okay, and the point is that this coarse structure is independent from S. Okay, there are more examples. Let's see. And there is another way of assigning a coarse structure to every metric space, and that's the C0 metric coarse structure. So what is this C0 business? Again, we have a metric space, and then E is a controlled, let E be a subset of X squared, then E is controlled, so E is in the core structure, if and only if the distance function on E, so this is the restriction of the distance function here, this tends to zero at infinity. So this is the geometrical idea. The distances between points is very close to zero when I'm far away. I need to formalize this. So being far away is being outside of compact sets, right? So what I want to say here is for every epsilon, there exists a compact set, compact subset, such that the restriction of the distance function to E minus k times k is less than epsilon. Okay, so I can read this as follows. So if x1, x2 is E controlled, so this is in E, and x1, x2 are not in K, or one of them is not in K, yeah. So either this is not in K or this is not in K, then then the distance between them is less than epsilon. Okay. Maybe we can see some example. This can be a bit obscure now. Let's look at the real line. So for the real line, what is the meaning? Let's take the real line with the standard metric. I will identify the real line with the open unit interval, but notice that the distances are distorted here. Yeah. 0 and 1 would be very far away from every point. So now some examples of controlled subsets are the following. So a subset of x squared, I can see it as a subset of this standard unit square, right? So what are some examples of controlled sets? These are controlled. Yeah, this is also controlled, right? Because if I take any product of compact sets, then the distance is going to tend to 0 outside of them. I'm too far away from the border. So these are examples of controlled subsets. And some examples of non-controlled subsets are the following. Here goes, for example, let's say the following. So this is again the unit square, and you see here, if I do something like this, approaching the border, then these points here will be very far away from those outside of every compact set. These are very far away. So this is not controlled. Right, and some similar examples with the same idea could be, who knows, this one. Let's say something crazy here, but then it goes to infinity over here. Then that's not controlled, or something like this. When I take a band, this is not controlled either. Okay, so some intuition. And then there is a way to connect topological spaces. So we can also use this coarse business with topology, and it's the following example. So there is another example here. We can also consider topological coarse structures associated to compactification. I will consider here any paracompact, locally compact Hausdorff space. So let's let X be a topological space. Is paracompact, locally compact Hausdorff. Note that this is very general. For example, every metric space, every proper metric space satisfies these assumptions. So by a compactification, what I mean is, well, a compactification is the following data. So I have a map from X to some other space. I assume that this other space is compact Hausdorff, and this map has to be a topological embedding. So topological embedding here means that it is a homeomorphism onto the image. Homeomorphism onto the image. And finally, the image has to be open and dense in this other compact space. Usually, I will not write this map. One usually does not write this map, this embedding, and just regard X as a subspace of the compactification already. We'll just write this. So, okay, now that I have a compactification, how can I consider a core structure? So let's talk about the corona. The corona of the compactification is the following space. Is the complement of the compactification minus this X. Okay, so this corona is the space of points that we're adding to X. We're attaching to X. So these are the points at infinity, right? Points at infinity. So following this idea, it should be possible to use this embedding to know when a subset of X squared is going far away in a non-controlled way, right? So I want to use this compactification to know which relations, which subsets of X squared are controlled. So that's what I will define now. So definition, let me move this here. So to the compactification, I will define the set of continuously controlled subsets, continuously controlled sets. They are controlled by the compactification. So the definition is as follows. A subset of X squared, so a relation is controlled if if I remove, I take the closure. So first I consider the closure of E in the compactification square. So I consider the closure in the compactification, then I remove the points of X like this. Yeah, and then this has to be contained in the diagonal of the corona. It has to be contained in the diagonal of the corona. So what is the meaning of this? We can write this in a different way. First of all, this complement is the same as the intersection of the closure of E with the corona times X union X times the corona. So these are the points of the closure such that one of the components is in the corona of the compactification. And this has to be contained in the diagonal. Means the following. These are the subsets of square such that if omega 1, omega 2 is in the closure of E, and either one of them is in the corona, one of them is in the corona compactification, then this condition that be the same. I'm getting to infinity, the components have to be so far. Is there any question?
Sorry, your voice got reduced again. So
Is there something that I should repeat?
now it's fine. No, it is fine.
Okay, I will try to remember them. Let's see some example. So, example. So I will consider the topological space R. So this is my topological space, but with two different compactification. So one of them is the Freudontal compactification. So the real line can be seen as a subset of the interval, the closed interval minus infinity plus infinity. This is this can be identified. It is the same as the following inclusion, right? So I can consider the open interval inside a closed interval like this. So this is called the Freudontal compactification of the real line. And what is the topological structure for that? Topological coarse structure. So let's see. Now I want to consider a subset of x squared, so of the plane, and I will see this plane inside inside a square. Okay, so this is the square of a closed interval. You can regard this like that. So now I consider the interval the interior of the square is the plane, and this side here would correspond to infinity times r. This side would correspond to minus infinity times r. This corresponds to infinity, r times infinity, and this is r times minus infinity. So this point is infinity minus infinity, is minus infinity minus infinity, infinity, and minus infinity, infinity. So now, which are the points of the diagonal of the corona? So it is this one and this one. These are the points of the diagonal. The diagonal of the corona is just these 2 points. So what I need is for E to be controlled, it is the same that if I remove the open part, so if I remove the part of E which is in the plane, it has to be contained in this diagonal. Okay, so in other words, at infinity, E can only touch this point here, this one, and this one. Cannot touch anything else. So an example here. Let's say I said E can do something crazy. Or in the middle, it doesn't matter. What is important is the behavior at infinity. So how does this E approach this boundary? So imagine it does something like this. Then, yeah, then you can see that the intersection of the closure of E at infinity with its contained. Example, this is something that is not controlled, it follows. This subset of string that's fine. There's no problem with that. There is a problem here.
Sorry, your voice is again breaking.
My voice. I will try to speak louder. Yes, so I was trying to point out some intuition behind what is topological. The idea is that is controlled if and if at infinity only touches the diagonal points of the corona. So on the left, this example.
No, it is breaking.
My voice is breaking.
Now it's fine.
Yeah, it's fine
Oh,
now.
I don't know why. Sorry about that. Yeah, so on the left, we see this set is controlled. On the right, however, this is not controlled because there is a point here at infinity, which is in the closure of E, but it's not in the diagonal of, yeah, it's not in the diagonal of the corona. Okay, so this is not controlled. Okay, so it's almost time. Next time, I'd like to introduce already what is coarse-cohomology and prove that it is an invariant. But I would use these last minutes for questions if you have any.
Could you please take up your slides? I just want to see some more. Yeah, so if you could go to the definition of course structure, and then I just hello.
Yes, yes, I'm listening.
So
You want me to go back to the definition, right?
yes, no, after that, these you said this bounded metric course structure, that is fine, and then you talked about examples. This is
Yes.
right. Yeah, so this is C naught metric course structure. Yeah, so could you please explain this why, like, it looks like that if so of course any bounded set is controlled, but from the picture it looks like every unbounded set is essentially uncontrolled in these examples, but so what I'm not getting the intuition behind it actually, that is why.
Oh, yeah. Also, for me, this is the hardest one. So let's look at it with more detail. That's a very fair question. So let's go to the same example again. For representation purposes, I'm identifying the real line with the unit interval, open unit interval. So bear in mind that the distances here are distorted. They are distorted. So let's think of now a subset of the plane. So yeah, a relation on R. So if I represent this in the plane, yeah, something like this. Oh, so something like this in the plane. So this is a tube, right? But this is now not controlled anymore, right? Because I can, no matter how big I take a product of compact sets, no matter how big I do it, let's say something like this, there will always be unbounded distances between points outside, right?
Yes, yes,
I guess that's the, yeah.
yeah.
I will think of, I want to think about this question in this case of an unbounded set. I will think about it. Yeah, I'm not sure about now.
Okay, no problem. Yeah.
Yeah, thank you. It's a fair question.
Are there any more questions?
May I ask one more?
Again?
Yeah, so I just, could you please explain this particular example with this diagonal thing and non-diagonal thing? Because I didn't kind of understand probably this definition of epsilon I in the right way or something. Here again, I have some problem to understand, kind of viewing pictorially it.
Yeah, you mean this specific one?
This specific example is an example whatever you defined before, right? Epsilon I control, uh, yeah, something controlled by I or something, right?
Yes. So
So
when is a subset controlled, right? That's the question.
yes,
So from the first definition, this would be the original definition. But I want to visualize it, right? So here I'm taking the intersection of the closure of E with the complement of x times x. So
yes,
this complement is exactly this one, right?
yes, yes,
So that's the outer square that we're looking at here.
yes, yes,
That's the outer square. So this condition now looks as follows. If I have a limit point of E inside this outer square, so that's like the corona of x squared, then the components have to be the same. It has to be in the diagonal. So in general, what I would do is I look at every limit point of E inside of the outer square. Here I have this one and this one. Both of them are in the diagonal, right? The two components here are the same. The two are the same here.
yes.
In this case, now, so this set is controlled. Okay. So far is this, yeah. Do you have a question in this left part of the example?
No. So that means if we take a subset in x cross x, and if it essentially towards infinity, if it goes to closer to the diagonal of the product, then that set should be controlled, right?
Exactly. The limit points, so getting closer and closer to the corona, These limit points have to be in the diagonal, exactly.
So this actually gives us an unbounded set which is controlled, right?
Yes, let me think of. We will see a definition of boundedness. So you see here, I'm not considering R as a metric space,
Yes.
but only as a topological space.
Right.
So
Oh, I see. Since you were saying R, we are identified with 0, 1, where 0, 1 is essentially kind of, there is no unbounded distance in that way, right?
there is no.
Like
Yeah,
0,
there
1
is
is
no.
essentially if I just, but we are not, so we are taking that that homeomorphism. Okay, I see. So, okay, so since what I want to say, let's say 0, 1 open interval and R, those two are homeomorphic as
Mhm.
topological space. But then I put my metric in 0, 1 by inducing the metric from R, right? So in that case, we can say things are bounded distance or unbounded. So if the things goes to a boundary, then those must be unbounded kind of thing, right? With respect to that metric.
Yes, yes, and but there is more, even more. We can describe the bounded sets only looking at the core structure. This is something we didn't see yet. We're going to look at this at the next one,
I
but
understand. Okay, okay.
yeah,
Okay.
sometimes in proper spaces, this is going to be a relatively compact space. So relatively compact subspaces are going to be the bounded, that's quote unquote bounded subsets. So yeah, what you say is true, and there is more. We can describe it without using the metric.
Okay. Thank you. Thank you so much.
Yeah, thank you for your question. So yeah, continue on the question. This is not controlled, as there is this point here that it's not in the diagonal, but it's in the closure of E.
Yes, because if we take any points towards this point, what you marked now, and any points towards this red point, diagonal point, beyond any compact set, the distance between them must be kind of bigger and bigger, right? That is why this set cannot be controlled, right?
I'm. Can you? I cannot hear you very clearly. Can you repeat it?
Yeah, so what I'm saying, so in this second example, if you take, if we take any compact set, right, how big it might be, but beyond that, if we take points from which are close to these off-white boundary point and points which are close to red boundary point, those two and then distance between those 2 points will be kind of bigger and bigger, cannot be controlled, right? That is why it is uncontrolled.
I see. Yeah, the distance. Yes, you can also describe this in terms of a distance. So this side here is r times infinity. And so this point I draw here is kind of x infinity for some real number x.
Yes.
And there is an extended distance on the horizontal compactification. Yeah. And you can still have a extended metric. It is the same as a metric, but can take infinite values. And then the distance between these two is infinite. Yeah.
Yes.
Yeah. But here the distance is 0. And in general, a limit point like this is at infinite distance of every other point except itself. Yeah. I guess this would be a way to formalize this idea. Did I understand your question right?
Yeah, essentially that, yeah. So
Mhm.
I just wanted to kind of convince myself why this second example is not controlled.
Agreed. There is, I think we were seeing this with convergence. There is a way of characterizing, so I will give a reference because I think it's very related to your question. So that's John Rowe, lectures on coarse geometry. This has to be in chapter 2. There is an alternative description of these control sets, which uses convergence of nets. In this case, it suffices to use convergence of sequences. So,
Yes.
and I think this is the idea that you're sharing here.
I see. Okay. Thank you.
Yeah, thanks for your question.
Yeah, I have a quick one. So, on a like whenever you in the epsilon I this thing, the control space you define, like whenever I have a topology, then I just have from the compactification I get a control system on X. Like if I start with a compact set itself with some topology, then is this epsilon I is something familiar to some known control structure?
Sorry, my audio quality is a bit weird today.
Oh, sorry.
If I understand well, your question is what happens if X is already compact, right?
Yeah, right.
I
So is
see.
this epsilon I something familiar?
I will. I can think of this now. If you give me a minute.
Sure.
So then every set will be controlled, right? Because makes sense. If X is already compact, X is bounded. So there should be nothing at infinity, right?
Yes, right.
And
Exactly. The diagonal is empty basically.
exactly. So now if X is already compact, this is empty always. And so this condition
Right.
is always satisfied. So every set is controlled.
Yeah, so
When
that's
every, yeah?
so that's nothing to like much to do with the topology unless the compactness like and yeah, so okay.
Exactly. That's an interesting question. Thank you. The idea here is in general, this is a family of subsets of X squared.
Right, exactly.
When in this case, when you ask, we have the equality. So every subset is controlled.
Right.
This means that X behaves like a bounded metric space. X is bounded. So from infinitely far away, this is going to be equivalent to a point.
Right.
So
So
that's why
like
everything is controlled. Yeah.
yeah, so is this something related to like you already in the previous lecture you told about like any finite group is like quasi-isometric to point like is there a like kind of geometric way what you did today for the covering space thing like for Z square or Z those are quasi-isometric to R by the covering space thing. So is there any way to see for the similarly for the finite groups? Like those are quasi-asymptotic to point by those constructs and so on.
Is there any way to see? Sorry, it's my audio. It is my audio quality. Is there any way to see exactly what? Sorry.
The finite groups, the quasi-asymptotic finite groups are quasi-asymptotic to points, right? That you
Yes.
said in the last class, yeah. So is there a way to see by the covering space thing what you did for Z or Z squared today?
Is there a way to prove this statement again, but using the Schwarzschild lemma, right?
Yeah.
I see. If G is finite, let's see. I think so. Let me see. If G is finite, then I can consider any finite generating set again. I mean, I could just take G, literally, right?
Right.
I could take a point, can I? Let me see. Sorry, let me go back. I think I can take a point. So this is finite always, and the action will be compact. Yes, so I think if G is finite, then the trivial action of G onto a point will satisfy the hypothesis of the Schwarz-Milnor lemma. So G will be finitely generated and quasi-symmetric to a point. Right? Let's check it.
Yes.
For the properness, like the trivial action would work in this case.
So let's see. I will compare. I will apply this theorem in this specific case. So
Okay, finite. Yeah, correct.
Yeah, since
Yeah.
G is finite,
Yeah.
everything will happen.
Yeah,
Finite.
right.
The symmetric space is just a point. So
Right.
it acts by isometries, right? For every compact subset of a point, so there is not much to do here. This is going to be finite, yes, because G itself is finite anyways.
Right.
And this is a point, so it is compact.
Yes, sure, compact, right. Yeah, thanks.
Yeah, thank you. Also an interesting question. Okay. Are there any more questions?
Okay. So if not, let's thanks to Sergio. And we'll meet again on next Wednesday at the same time. So see you next week.